Hello dear students, in today's video I'll explain about depression and freezing point. Okay, so let us see what is the freezing point. So freezing point is defined as the temperature at which liquid changes into solid. So for example, I am taking some water in a container and I am keeping in a refrigerator. So it is changing into solid ice at some temperature. The particular temperature is called as the freezing point. So already we know below 0 degrees centigrade water gets freezed. So that point is called the freezing point of water. Okay, so now we can define this freezing point in another way. The point where both solid and liquid coexist and have same vapor pressure. So if you observe any solid ice, you can see both solid and liquid coexist with each other and they'll have same vapor pressure. So this is also one of the definition of the freezing point. So we can say one more thing, that freezing point of a solution is always less than solvent. So why? This is called as a depression. So depression means decrease. So let us see what is the depression in freezing point. So firstly, I am taking a container. You can see the container here, beaker. In beaker we are having water. Okay, so whenever I decrease the temperature, all water molecules, because of hydration energy, comes closer and hydrogen bonding takes place between them and comes closer and becomes a solid ice. Okay, so now when I add any solid to this water, that means when I am making this as a solution, I added some solute to the solvent. For example, I added a sodium chloride. You can observe sodium ions and chloride ions in this solution. So what will happen when I decrease the temperature? These water molecules comes closer, but these sodium and chloride ions interrupts this hydrogen bonding. That means what? In order to bring them close, in order to bring this solute and solvent molecules together, I need to decrease the temperature more when compared to solvent. Hence, we can say that solution's freezing point is less when compared to solvent's freezing point. This decrease is called as a depression and freezing point. Okay, so now, for example, I'm plotting a graph between vapor pressure and temperature by taking two solutions and solvent. You can observe that solvent and solution 1, solution 2. So I'm drawing a vapor pressure this side and temperature this side. So vapor pressure of solvent beginning, solvent will have vapor pressure more and solutions will have low. So you can observe that solvent's freezing point is TF. Pure solvent freezing point is TF. T1, T2 are the solutions freezing points. So when compared to this solvent's freezing point, you can observe solutions freezing point is less. Okay. From this diagram, you can get two triangles. Actually, we are getting three curves and two triangles. Triangles you can observe BEC and BDF. Okay, BEC one triangle, BDF one triangle. So from BEC and BDF, EC by DF, you can observe EC by DF. Okay, EC and DF are similar. So EC by DF equals to BE by BD, BE by BD. Okay, so now EC means you can observe EC TF minus T2. Okay, DF means you can observe DF TF minus T1. Okay, and BE means you can observe BE. BE means what? P0 minus P2. BD means P0 minus P1. Okay, so now from this we can say that it is a difference. So delta T2 by delta T1. That is the vapor pressure difference. So delta P2 by delta P1. So from this what we can see, delta TF is directly proportional to delta P. That means depression in freezing point is directly proportional to the relative lowering of vapor pressure. Okay, so we can consider this as equation 1. Let us continue the derivation. We got the equation 1. Delta TF is directly proportional to delta P. That means depression in freezing point is directly proportional to the relative lowering of vapor pressure. So, but according to Rolle's law, already we know relative lowering of vapor pressure is directly proportional to the mole fraction of the solute. Okay, so already we know delta P is directly proportional to small n by capital N. So small n value already you know what is a small n? Number of moles. Number of moles formula weight by molar mass. So I'm substituting that formula in this. Okay. Small n means small w by small m. Capital N means capital W by capital M. Okay. So from this I'm getting this next equation. Okay. Delta P is directly proportional to small w into capital M by small m into capital W. So for a given solvent, M is constant. So mostly we know solvent is major quantity. For example, I consider solvent as water. So molar mass of solvent is always constant. It won't change. For example, I can tell you molar mass of water is 18. So I consider this as a constant. So I remove this M from this equation. So delta P is directly proportional to W by small m into capital W. This is considered as equation 2. So from equation 1 and equation 2, we are getting equation. Delta TF is directly proportional to small w by small m into capital W. So delta, this one is equation 1, this one is equation 2. So from this I am getting the equation, new equation. Okay, so now what we will do, delta TF is equals to, I am removing this proportionality symbol and I am keeping a constant KF, small kf. Okay, so delta TF is equals to small kf into W by small m into capital W. So Kf is a freezing point constant or cryoscopic constant of a solvent. So freezing point constant. So now to this equation I am dividing this side with 1000. I am multiplying this side with 1000. So delta TF is equals to Kf by 1000 into W into small w into 1000 by small m into capital W. So small Kf by 1000. That means depression of freezing point per 1000 is called as a molar depression constant. So I am substituting capital Kf. Delta TF is equals to capital Kf into W into 1000 by small m into capital W. So Kf is molar depression constant now. So already we know this formula indicates a molality. So molality, Kf into molality of solutions. Finally we got this equation. Depression in freezing point is equals to molar depression constant into molality of solution. So from this equation, if I want to calculate the molar mass of a solute, then I can bring this equation, small m is equals to Kf into W into 1000 by delta Tf into capital W. So simply I am bringing this m this side, delta Tf this side. Okay, so finally I got the relation between molar mass and depression in freezing point. So this is completely about depression in freezing point definition and derivation of the depression in freezing point. Thank you so much for watching.